In the previous video, when we were solving systems of linear equations, we solved it doing it in this way where we separated. We wrote the a times the x equals the identity, and then we wrote two systems and then solved using Gauss-Jordan elimination. Now, rather than solving the two systems represented by this way, separately, you can solve them simultaneously by adjoining the identity matrix to the coefficient matrix. So notice these are the same numbers on this side, and it's just these numbers that are different. And so notice we just put it all the way over here. So 1, 4, -1, -3, and then the the identity matrix on the right side. This doubly augmented matrix can be represented as A and then dot dot I by applying Gauss-Jordan or dashes. By applying Gauss-Jordan elimination to this matrix, you can solve both systems with a single elimination process. So notice we set it up here, and then they just added, or we can add row 1 and row 2 together, and we get 0, 1, 1, 1. And then we multiply -4 to row 2 in order to get the identity matrix on the left side. And so here is the inverse, -3, -4, and 1, 1. So it's a shorter process. So let's use that now. So finding an inverse matrix, let A be a square matrix of dimension n by n. So remember, it has to be a square matrix in order to be able to find the inverse. And then write the n by 2n matrix that consists of the given matrix A on the left, and then n by n. Identity matrix on the right to obtain A, and then the dashes I. If possible, row reduce A to the identity using elementary row operations on the entire matrix. The result will be the matrix, the identity, and then the inverse of A. If this is not possible, then A is not invertible. So for example, on the left side, you find you get 0, 0, 0, then you know that it is not possible. Then you can check your work. You can always check your work to multiply. So multiply A times the inverse of A, and you should get the identity, and then the inverse of A times the matrix A, and you should get the identity again. Let's try that here. We have A, and then the dashes, and then I. So that's how we're going to set it up. So we have 1, -1, 0, 1, 0, -1, 6, -2, and -3. On the right side is our identity, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so let's use Gauss-Jordan elimination in order to solve for our inverse. And so one thing we can do, so I want to get rid of the one in the second row. And so one way to do that is I'm going to go ahead and multiply the top by a negative and then add it to row 2. So this will be, I'm just going to do the work here, negative, positive, negative, and then we'll add that. So, oops. So my first row is 1, -1, 0, and then 1, 0, 0. So the second row becomes 0, 1, -1, -1, 1, and 0. And the last row is still 6, -2, -3, 0, 0, 1. So then I want to get rid of the 6 in the bottom. So I'm going to multiply, let me notate my work, minus row 1 plus row 2. Then I want to multiply this top by -6 and then add it to here. So -6 row 1 plus row 3. So -6, +6, 0, -6, 0, 0. And so that'll get us a new row 3. And then, so that is 0, 4, -3, -6, 0, and 1. Okay, continuing on, what we want to do is to get rid of this 4 here now. So I'm going to multiply the top one by -4. So that's 0, -4, 4, 4, -4, and 0. And I'll add that to row 3 here. So copy everything over. And then so we get 0, 0, 1, -2, -4, and 1. Clean this up a little bit. All right, so now we just keep on going. So we got that by -4, row 2 plus row 3. So in order to cancel out the -1 here, so I'm just going to add row 2 plus row 3. So that will be 0, 1, 0, and then -3, -3, and 1. And then write the last row, 0, 0, 1, -2, -4, and 1. And then now we want to get rid of this 0, so let's add row 1 to row 2, or row 2 to row 1, whichever way you want to think about that. So that becomes 1, 0, 0, and then this is -2, -3, and 1. So we get 0, 1, 0, -3, -3, 1, 0, 0, 1, -2, -4, and 1. And so this here on the right side, so notice on the left side we now have the identity, and on the right we have the inverse of A. So the inverse of A is, or A inverse is -2, -3, 1, -3, -3, 1, and then -2, -4, 1. And then again, you could always double check by multiplying A times the inverse of A, and that should get the identity, and then the inverse of A times A, and you should get the identity as well. So try this example here. Find the inverse of A. Okay, if you tried this out, you should have gotten your inverse as -4, -2, 5, -2, -1, and 2, and -1, 0, and 1. And again, you can always do a check. A times A inverse should equal the identity, and A inverse times A should equal the identity. The process shown in example 3 applies to any n by n matrix A. When using this algorithm, if the matrix A does not reduce to the identity matrix, so it doesn't work out, then A does not have an inverse. So this one does not have an inverse. To confirm that this matrix has no inverse, adjoin the identity matrix to A to form A and then the identity, and try to apply Gauss-Jordan elimination to the matrix. And you'll find that it's impossible, so you may find that.